In the last video, I looked at using a summary measure for a 2x2 contingency table called relative risk. And in this video, I'm going to look at an alternative to relative risk called the odds ratio. And it's very similar, but it is ever so slightly different. So if I just quickly go back and look at what we did in the last video, we looked at this experiment where we were looking at women that were given either an aspirin or a placebo, and they were tracked over 10 years, and the researchers recorded whether the women developed invasive cancer or not. And this was the contingency table that resulted from that experiment. And in the last video we went through calculating the relative risk of developing cancer for someone getting aspirin relative to someone getting the placebo treatment. And so the way that we calculated this was to break down the table into the different values. So this was our table here, and we call this number A, and we call this number B, and we call this number C, and we call this number D. And then the relative risk was given by this formula here. So we could think of this part of the formula here. So it's 1,438 divided by the sum of 1,438 plus 18,496. We could think of that as the estimated probability of a woman developing invasive cancer if they were given the aspirin treatment. And so what I'm going to do is I'm going to give that the name P1 hat, and we'll just see that this is the estimated probability of a woman developing cancer if they're given the aspirin treatment. And so the notation here is P1 is standing for a population probability or a population proportion, and the hat is just indicating that this is an estimate from a sample. And so the other estimated probability is P2 hat, and so that was the estimated probability of developing cancer for someone in the control group, the placebo group. And then the relative risk was I'll just type this in, P1 hat divided by P2 hat. That was the relative risk. So far I haven't done anything new. I'm just repeating what I did in the last video, but I'm just using slightly new terminology and notation here because we're going to make use of that when we define the odds ratio. So P1 hat is a estimated probability. And it represents the probability of a woman developing cancer if they're in the aspirin group. We could also think of the odds of a woman developing cancer if they're in the aspirin group. And the odds of an event happening is equal to, it's defined by the probability of that event happening divided by 1 minus the probability of that event happening. So that's what is known as the odds of the event happening. And so if I calculate that ratio, P1 hat divided by 1 minus P1 hat, so that's the odds of a woman developing cancer if they're given the aspirin treatment. Okay, so the odds in this case is 0.07774654. We could also calculate the odds of a woman developing cancer if they were given the placebo treatment. They're in the control group. So that's That's this ratio here. Okay. We can take the ratio of these two odds, and that gives us something called the odds ratio. So that's what this calculation is doing here. Okay, and then in this case, the odds ratio is equal to 1.008744. So if we think back to the last video, we have relative risk, and then what I've just described just now is the odds ratio. So these are related ideas, but they are different. And they are both ways of summarizing a 2x2 contingency table. And so that's the focus in this video, is the odds ratio rather than the relative risk. This looks like a fairly complicated calculation. If you were to just do some pen and paper calculations and work with the equations, you would actually be able to simplify the calculation to this. It ends up the same. So this is just like a shortcut formula. Okay, so that tells us the odds ratio, and so it's the ratio of the odds of a woman developing cancer in the aspirin group relative to the odds of a woman developing cancer in the placebo group. Okay. Just as in the last video, when we thought about the relative risk, recognizing that, as usual, we have a situation where we have a sample and we're trying to make an inference about a population, so we have sampling uncertainty, and to quantify that sampling uncertainty, we calculated a confidence interval. And so we can do a very similar thing here. We can calculate a confidence interval for the odds ratio. And so just running through that calculation, just as with relative risk, we actually calculate a confidence interval for the log odds ratio and then exponentiate the lower bound and the upper bound to get the confidence interval for the actual odds ratio itself. So that's what these calculations do. This is the standard error for the log odds ratio, and then this piece is the lower bound for the log odds ratio, and if I exponentiate it, it's the lower bound for the odds ratio itself, and then this would be the upper bound for the log odds ratio, and this exponentiating that number gives us the upper bound for the odds ratio. So we can say we're using a critical value from a normal distribution for the 97.5th percentile, in other words 1.96, so we're talking about a 95% confidence interval here, and we could say we're 95% confident that the odds in the population is between 0.935 say and 1.088. So that's how to calculate confidence interval for the odds ratio by hand, going through all these calculations. So it's a little bit tedious. It takes some time, lots of scope for making calculation errors there. So again, there's a function that does all these calculations for us, and again, it's in the EpiTools package, and this one's called odds ratio. So I could look up what that function does. So it tells us it's odds ratio estimation and confidence intervals, and here's all the gory details. So in this case, I can run this code to calculate the odds ratio and the confidence interval and a whole bunch of other stuff. But if I just pick out this part of the output, I get the estimated odds ratio here and then the 95% confidence interval here. So that's how to calculate the odds ratio for a 2 by 2 contingency table, and also a confidence interval for that odds ratio.